Okay, let's go and get started with the lecture today. Happy Thursday. Hope everybody's getting caught up on the labs. We are going to go through the lecture today. We are not going to have a new lab today, which hopefully will give you the chance to get caught up. But let's go through our material today. It shouldn't be too long, not a lot of slides here, but I do want to get through this material. All right, so let's go ahead and talk about this. So the idea is, quick review, we've had a number of synchronization mechanisms that we've looked at for synchronizing one process with another one, or one thread with another one. We've had locks, recursive locks or RLocks, semaphores, and condition variables. And each of them offer a subtly different capability, and really each of them has like a subtly different use case. Like for example, locks have a simple acquire and release. The same thread that acquired them had to release them. Our locks are the same, but if you have that one thread could acquire a lock multiple times as long as it releases it the same number of times. A semaphore has an acquire and a release, but it could be acquired by one, released by another, and it also has a value associated with it. So it's not Boolean. It's not just on or off or acquired or not acquired. You can assign a value and have it be able to be acquired a certain number of times before it locks, and then you'd have to any subsequent attempts to lock would then block after the value gets to 0. So semaphore is kind of like a countdown variable that then locks once the countdown gets to 0, and then acquire and then release kind of increments it back up again. And it also has an effect of a different thread could lock it or acquire it, then could release it. And condition variables are similar to locks, except they can wait. They have a wait method as well, and they can wait. When they do wait, they release the lock. When they're notified, they reacquire the lock before proceeding. So it's kind of like a way to have that conditional waiting, or a buffer that says when the buffer's full, don't allow anything else to be put in it. So it blocks at that point. Or when the buffer's empty, allow anything to be taken from it, but as soon as it's empty, then we block on it. And you've probably seen that with code you've written. If you go to, for example, in a programming environment like the Arduino, if you do a serial.get to get a character from it, it'll, actually that one does not block, but there are implementations of things like that. When the buffer's empty, it blocks until it gets a character to proceed. Now, today we're going to look at a few more synchronization mechanisms and then one final bonus thing at the end today. The thing we're going to start with is events. And an event is a really simple synchronization and communication mechanism that essentially acts like a flag. So kind of like a flag variable that you either raise, set it to 1, set it to 0, and it's Boolean like that. It is either 1 or 0, or true or false, which means that the operations on it are either you could set it, meaning raise the flag, or you can clear it, meaning lower the flag. And that flag variable itself, the value of it is actually encapsulated or stored inside of an event object instance. So inside of that event, we have the values being stored. And so we don't really touch the value directly like you would with a shared variable. You wouldn't say like flag equal 1, flag equals 0. We interact with it through methods. So let's take a look at those methods that are available. So objects in Python. First off, to create one, it's in the threading module. So you do threading.event. And then in the set of methods that we have here, event1.set, event1.clear, event1.isSet, event1.wait. So essentially what those do is set raises the flag, or raises the value of that event's internal flag to 1, to true. Clear sets it back to false. It's important to note that when you first create one of these events, and it's initially false, so it's not set initially. So the flag, when you create it, think about it as you initialize the variable to 0. And then when you do a set, it raises it to 1, or true. And when you clear it, it goes back to 0. And those are the only two values you're allowed to have for an event, either set or clear. Now you can call this isSet, and it'll return the value. So if you call isSet and it's set, you'll get true. If you call isSet and it's not set or it's cleared, you'll get false. So it's essentially just returning the value of that event. Now you can also call, and this is the one where it gets to be more useful for threads and not just like a weird shared variable hidden inside of an object, is you can call this wait method on it. So you could say event1.wait. And when you wait, it'll block as long as the flag is cleared or the value is false. And as soon as it goes to true, it'll unblock. Now, this is a little bit different than other things that they would block and then wait for example, a condition variable where it would perform a wait and then it would be notified and then continue. And the difference here is, well, let's take a look at that. Also, you can specify a timeout for how long to wait. Default is none, so it will wait forever with a timeout of none. But if you specify timeout of like 1.0, it'll wait for 1 second and then give up on the wait. Now, how is it different to wait here relative to the wait and notify we saw with condition objects? And what makes this different is events, there's no lock associated with it. There's no mutual exclusion enforcement associated with it. It's just like this flag variable. And you can either set it low or you can set it high. And what that means is if you have two or more threads that are, or one or more threads that are waiting on that event, when that event gets set, all of the threads can unblock. So it's not like with a condition variable, one of them proceeds and there's mutual exclusion. They can all proceed. So no matter how many threads are waiting on that event, when we do a set and the flag goes to 1, they could all unblock to proceed. So it's a very simple way of having one thread perform the set and have the other ones that were waiting then get that event and proceed. So it's a simple form of thread synchronization where you can have one thread block or multiple threads block and then another one say proceed and they continue on. All right, an example of where you might use that would be something like a 2-player game. So imagine you have this 2-player game with has 2 threads, one for each player, and each thread has to wait until the main thread loads up everything for the board and gets everything ready, and then the main thread says go, and they all start at the same time. So imagine like a racing game or something like that, where each player has a different car, and each car is governed by its own thread. Maybe it's like a split screen racing game where you can see the driver 1 on the top, driver 2 on the bottom. But you want both, and those are easiest to do by just making threads for each of those. And then you just want the race to start at the same time for both of them. So you basically make both of those threads wait on some global event object, and then once the main thread is ready and it's time to start the race, the main thread sets the event flag, which unblocks the ones that were waiting, and they both start. So let's look at some code that kind of embodies that. All right, so here's a little bit of code. Now, obviously, this isn't a full game. There's no graphics in this. There's no game logic or anything like that. This is just to show you kind of how it would work. But notice that here, I've got this event that I called event_go. So that's my go event. And what happens is I have 2 functions, player 1 and player 2. And I start a thread for each of those. So both of these functions can be considered running concurrently after they're started. But the first thing they do is they might load their screen or get ready or something, but they'll hit this event_go.wait. So they will both block at that first line there. So the game loop hasn't started for either of them. They're waiting. But then down here, the main sets up the game logic, does whatever it needs to do, and then it sends this event.go or event_go.set, which raises the flag, which unblocks both of these at the same time. So now both player 1 and player 2's main loops start running concurrently, and they start at the same time. Now, after this is done, the main loop finishes, we can join with both of those. There'd be some logic to exit this, presumably, but that's the idea, is this one set unblocks both of these simultaneously. All right, now one more thing we're going to cover today. So that was events, and those events are very simple, much simpler than other synchronization mechanisms. It's just like a flag. It raises. Anything that's waiting when that raises continues on. Now there's another type of synchronization mechanism that's kind of related to that, called a barrier. And what a barrier is a barrier waits for a certain number of threads to reach the barrier, and then it automatically releases all of them. So it's kind of like an event that can count up how many things are waiting. It says, okay, 1 thing is waiting, 2 things are waiting, 3 things are waiting. Let's say it's a 4-player game. 4 things were waiting. Now I have 4, so now they can all be unblocked. And one of the things to note with barriers is all that matters is the number of waiting threads has to become greater than equal to the barrier count, or the target that it's of the number that it's waiting for to unblock. And so once that number is reached, they all unblock simultaneously. There's no signal that's required. There's no set that's required. There's no notify that's required. There's no, it happens automatically, and all that matters is that the right number of threads showed up to wait on that, and then it unblocks it. And you might think of examples of something like that where a certain sequence of events has to happen that are maybe concurrent with each other, but then you want to synchronize everything at some point, and then branch back out, maybe have things happen concurrently again, and then synchronize again at some point. So let's look at how barriers work in Python. And in Python, essentially to create a barrier, it's the same thing as all the other objects, threading.barrier, and all you pass into it is how many threads you want that barrier to be associated with, that once they await, it'll unblock. So if you put 2 there, thread 1, thread 2 would hit that barrier, and as soon as 2, they would both unblock at the same time. But if we put 10 in here, it would have to get 10 threads that wound up waiting on that barrier before it unblocked. So it's kind of like a weird gate that if enough people are pushing on it, it falls over. But you can specify what number you want. Now that returns this barrier object. There are a couple optional parameters. There's an action, which allows you to put a reference to a function, like a function name there, and that function can get called whenever the barrier releases. So that could be something like to log something to a file. There are cases where the action here resets the barrier automatically. So the barrier breaks, everything proceeds, and then the barrier automatically resets for the next time. There's also a timeout, just like with the other wait functions, where you can set up the barrier. So how long do you force everybody to wait before the barrier automatically releases without that number? Okay, other things for how this is used, barrier.wait. So we do barrier1.wait. On any barrier object, that waits for the count to be met. So that will block all of them just like an event did, but the thing that unblocks it isn't a set, it's just the quantity that are waiting. Barrier1.abort, that'll break the barrier for all of the calls or all of the threads that were waiting on it. And you can tell the difference between a barrier that was successfully had the number reached or it was broken by abort, because it'll throw an exception in the broken barrier area. Now you could, if you wanted to, catch that exception and ignore it, but usually you want to know the difference. Did everybody reach here, or did something else go wrong and somebody aborted it? And the reason for abort is to eliminate the situation where you might have multiple threads waiting on something, and then you realize, well, one of the players left the game, and so we don't want to necessarily release everybody for a 4-player game when there are only 3 people left. So we might need to abort that and have those functions say, oh, there weren't enough players, something bad happened by catching this exception. Now also you can check the state of the barrier, whether it was broken or not, by reading barrier1.broken. That would be true if it was broken. That'll read false if it's not. And then parties is the number needed that you pass in up here, the number to wait upon. And then n_waiting is how many people are currently waiting on it. And then obviously with a barrier, think of it like that fence that tips over, you can reset that by barrier1.reset, and that'll set back up so things can start building up on it again. Oop. Here we are. Now, what's the main use case for barriers? And I apologize for the small font on this, but I wanted to fit that diagram on here. But the barriers can be used for ensuring synchronization along some chain of events. And so one example might be making sure all the players completed level 1 before proceeding to level 2. And maybe, I don't know if anybody here has played that game Jackbox, but you have things where it branches out, people do things independently, but then it gathers their data and it has to wait for all of the players that are playing to check back in and have all of their stuff. So a barrier might be a good thing for something like that. Other things, anything that has like processing stages, where this might be like a render farm or something like that. We have all these different threads, and you do one stage first, and then that hits that barrier to make sure everybody has completed stage 1. Again, kind of like a game. Everybody's completed level 1, go to level 2. Everybody completes level 2, go to level 3, and so forth. And that ensures that, especially in cases where you need the data from the first stage to know what happens in the next stage, to know what happens in the third stage. Like Jackbox, you have to know who picked what and did what questions here to know what to do in the next stage and who has what points. And then from there, you have to know who won that round to know who goes on to the next round, and so forth. But at the end, if we have these barriers, that'll ensure that stage 1 happens and finishes for everybody before we go on to stage 2, which happens and finishes for everybody before we go on to this. And then we want to make sure that everybody else finishes before we gather the results down here at the bottom. And that's a pretty common use case for barriers, is ensuring that you have some sort of a like lockstep between each of the stages. And it's a very convenient way to do that because it naturally releases on its own. We don't have to basically check a whole bunch of different flags or have some semaphore that counts down or up or some other weird logic. The barrier handles all of that for us. Okay, one more thing. So this is I promise this is the last one more thing today. And that is, if you look at a timer object, they're not really a form of multi-threaded synchronization. They're a form of like synchronizing a thread into the future, having it delay itself for a certain amount of time. So timer objects allow a thread to be activated only after some specified amount of time has passed. And that would be equivalent of like an alarm clock, or you have your phone and you want to set like a timer on it. And after a certain amount of time, the timer wakes up and does something and goes beep. So the way that works is threading.timer. You pass in the interval, in other words, how long to wait, and then the reference to the function you want called after that amount of time. Now you can pass arguments to that function. There's also this keyword argument thing where you can pass in a dictionary of the arguments rather than a tuple like over here. But notice the main thing here, the things that are required, you have to say how long into the future you want this function to be run. And then once that thread is started, the timer will count, and then when this time elapses, this will get executed once after this number of seconds have elapsed. All right, let's look at an example of that. All right, so here's an example that I basically just, after 30 seconds, it prints game over. So in this case, what happens is we have timer 1. Timer 1 is set up to be threading.timer with 30 seconds. And then when it's done, after the 30 seconds, it's going to call time up. So what's going to happen when I run this, it's going to print game on, start that thread, and then exactly 30 seconds later, we're going to get printed out, game over, and then thread 1 that joins is going to allow it to continue. So this is giving like that 30-second delay before it does that. Now another use case for timers is what if you want something to happen periodically or repeatedly. So periodic actions are possible as well, but in order to do periodic actions, we have to do something a little bit, it seems a little clunky to me with this, and that is, and there's an indentation problem on this code. Let me fix that real quick. Okay, but essentially what it does is this works the same way. Oh, there's another indentation problem. What the heck happened here? That needs to be over there. Let's move that up there. All right. So I have defined this tick function, and what it does is it has this global count, which means I'm accessing this global counting variable. I'm adding 1 to that. And if we have more than one of these things running this function, we maybe want to protect that with a lock or something like that. But for right now, we'll just leave it like that. But then we print out tick. That's all it does, is print out tick. And what happens is if the count is less than 10, then notice I'm making a new timer object and starting it all in that one line with the same function that I have here. So in other words, this function right before it terminates starts another timer to call itself. And then that one, after a second, is going to, and we know that's going to be a second because there's that 1 there. So 1 second later, it'll call it again. And the next time it'll add to the count. It'll say, hey, if I'm less than 10, then set myself up to be called again. So it's kind of like saying its alarm rings and it sets itself up for a new alarm. It's kind of like hitting the snooze button. So it says tick, hits the snooze button for 1 second. Wakes up, says tick, hits the snooze button again. And that will happen up to 10 times in this example. And you can change this number, or you could take this if statement out completely and have it happen forever, as long as the program is running. Now, there are other ways to have periodic events like this. We just set up a thread that has like an infinite loop inside of it, and it does a sleep. So if you want something to happen every 10 seconds, you could say sleep time.sleep 10, do your thing, and do that in a loop. So it does its thing, sleeps for 10 seconds, does its thing, sleeps for 10 seconds, and just repeats that. But this actually uses a timer to do it. And so down here, I made it so the main loop will run a total of 10 times, doing nothing here, waiting for that count to get to be 10. Then it prints out down here. We could have put its time.sleep in there. But let's just, let me actually run that code here in a second. And I need to fix this again here. Hold on. I don't know what happened when I pasted this in here, but it's not good. All right, there we go. Okay, so we're going to try this code here in a second. But one thing to note is that since timers are executed just as threads, they're just a thread that's running, that means they can make use of any of the other thread synchronization functions. And you can have multiple timers all going at the same time. In other words, I could say, make this event happen. I don't know, let's say if it's a game, make this event that opens this, opens the gate to the dungeon after 20 seconds, make it so the lava starts rising after 30 seconds, make it so you can schedule those events into the future with this thing. And it's very easy to do. Really easy logic there. Okay, so that's all for today. But before I say that, let's go ahead and look at that code and actually run it. I believe I have that up here. Let me switch over so you can see what I'm doing. Okay, so here's that code that we just looked at. And you'll notice that in here, again, import threading, tick, we're going through that stuff. And then down here, we're basically just saying, hey, well, the count is less than 10. And I think the only difference here is I'm going to add that print statement on the end to say print done. And let's run this and see what happens. So tick, count those 2, 3, 4, 5, 6, 7, 8, 9, 10, done. Maybe I should have noticed that that was a little bit weird to put that on the same line. We might get that different next time because that means that this print here hadn't quite finished when the count reached 10. And this is actually a synchronization problem that we're seeing here. That we have that count plus equal 1, that happens, which unblocks this. And then both of these are trying to print together. So we might get the last tick printed after the done or before the done or on the same line as the done, because there's a race condition right here. When that count goes up there, this print and that print can overlap each other. So to fix that, maybe we should move this before that up there. Let's see if that helps. Okay, now we don't have that race condition anymore because we've already finished printing tick by the time that we changed the count. So that was, see, again, the concurrency is tricky business. You got to watch out for things like that, that this variable changing unblocked this. And maybe a better way to do this would have been to make an event and have it so that when this gets to the end, when that does get to 10, when the count gets to 10, then we release the event. And that would also eliminate this busy wait loop we have down here. So let's go ahead and do that. Let's change this real quick. We haven't written any code that uses an event, so let's do it. All right, so up here, let's do event 1 equal threading dot event. And then down here, rather than this wait loop, let's do ev1 dot wait. So we're waiting on that event. And then what's going to get that to complete is the else of this. If it's not less than 10, then it has to be equal to or greater than 10. So here I'm just going to do ev1 dot set. So we set the flag there. So same behavior, but we got rid of the busy wait loops. This is actually using less processing power now because we're not constantly in the main going, is it done, 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 tick, is it done, is it done, is it done, is it done, tick. We're just saying, wait, the main thread is blocked, not doing anything until that event comes through. All right, so back to the presentation for just a second. Like I said, no lab for today. That means you should really work on finishing up your other labs, getting those done. And then next class, we're going to look at using multi-threading to actually improve performance of a program. So for example, if you think about a program like the Google has a spider that spiders all these sites on the internet and downloads pages and indexes the contents, that's clearly something that has to be very efficient. And it's also clearly something that has to be done concurrently. You couldn't have a single processor, a single system doing all of that work for the entire internet. And so that's the kind of thing that maybe downloading things, is there a way to make it faster? Is there a way to get the download to be more efficient and faster than if you run a single-threaded version of that? Now, there are cases where you try to make a multi-threaded version, and it actually makes it slower because the overhead of farming it out and getting the answers back can actually hurt performance. Okay, so let's go ahead and stop there. Everybody stay safe, wash your hands. Relatively short lecture today. And I did that because I want you to have time to work on those labs. I know that some people are a couple labs behind. If you're late on those, go ahead and get them in because I'm going to try to get those graded. At least the ones that are due, get those done because I'm going to try to get those graded coming up here. And I really don't want to grade them and then maybe go over it if you haven't done them yet. So try to get those done and stay safe, and I'll see you next time.